Okay. So welcome everyone to our second talk. We have Olexei who's going to talk about studies of deconfined quantum criticality in 1D spin chains. Thank you very much, Olexei, for coming, and please take it away.
Okay, I want to first thank the organizers for invitation to this workshop and opportunity to present our work. So I will talk about our studies of deconfined quantum criticality in one-dimensional models, and this will be based on these three papers. And I want to acknowledge people who really did all the hard work behind these papers. Is Shenhan Jiang, who was postdoc at Caltech, and my former student Brandon Roberts. So, the clicker worked, but now it's. Let me try. Okay, so here is outline of the talk. So as a background and motivation, I'll do a quick recap of deconfined quantum critical points. I will refer to them as DQCP, and in the context where this was first proposed on for spin halves on the two-dimensional square lattice, with SU2 symmetry or with U1 symmetry. And I'll spend a little bit more time on this U1 or easy plane case since it will actually be, it will motivate the one-dimensional model, the first one-dimensional model that I will discuss, and there will be a lot of parallels with this easy plane case. So then I will spend first part of the talk on Ising like one-dimensional model of DQCP, where we will see a continuous ferromagnet to valence bond transition in a spin 1/2 chain with Z2 symmetries. And I will describe analytical theory and also numerical studies of a concrete model. And then I will discuss in the second part an almost DQCP in a spin 1 system with Z3 symmetries, and almost here is that actually we suspect that it's first order because we have just one point on the phase boundary that is exactly solvable but has like correlation length of 200,000 lattice spacings. And I will here I will spend more time on numerical studies since we do not have as much analytical theory. I will give some theory of whatever we can do, and then I will describe this integrable model which we happen to have here, and some scenarios why we have such long correlation length. And I will give some conclusions separately for each part as I speak. And roughly I anticipate the first part should take under 1 hour, and the second part should take like 45 minutes, but let's see how it goes. So here is background. So the DQCP refers to possibility of a direct continuous transition between phases with incompatible order parameters. So Landau would say this transition has to be first order, but it was proposed that maybe in quantum systems these transitions can be continuous. And the specific example is transition between Neal and VBS phases of spin 1/2 on the two-dimensional square lattice. And the hallmark of DQCP and the original theory of this DQCP had this feature that the natural variables to describe the transition are fractionalized fields that are absent on either side of the transition. And this was proposed back in 2003 by Santil and all, following some prior work by Anders, who is in the audience, and there have been many subsequent theoretical and numerical studies of this phenomena. One of the interesting findings, also initially by Anders, in that model with SU2 symmetry, apparently at the critical point, apparently the three-component Neal and two-component VBS order appear to be unified into five-component order parameter, and there is emergent SO5 symmetry, and this also gave inspiration to many recent developments. Now, unfortunately, it seems that this scenario cannot be realized with the symmetries of bootstrap seems to rule out CFT with the symmetry and the critical indices that have been extracted from these numerical studies. And there have been some proposals how what looks in numerical studies like continuous transition on very large systems may be pseudo-critical. And now, yes?
Some dumb basic questions. Landau would allow two second-order.
Yes, there would be
some intermediate.
Yeah,
and you could then fine-tune so those two come together.
Yes, but that would be an example of a multi-critical point. And I guess this original proposal was that this is a generic transition.
I see.
So.
And the novelty is that fractionalized phases means deconfined gauge fields that emerge.
Yes, so the deconfined refers that the natural variables in these original proposals were fractional, like fractionalization of the Neal order parameter.
Fractionalization always happens through gauge dynamics.
Yes, there would be the theory for the transition was gauge theory. Yeah, so our motivation is to see if one can realize some similar physics in one dimension where we have access to more tools, like Bostonization, which will appear, and numerics is easy in one dimension, and so on. Okay. So let me review this DQCP.
Sorry,
yes.
I have another question. There was a paper that excluded SO5 symmetry from the bootstrap constraints. I forgot who was the author at the moment. Are you familiar with this paper?
So yeah, that's what I said here. That the bootstrap seems to rule out.
Oh, sorry.
Yeah.
Sorry, I was responding to an
Yeah, that the critical indices that have been measured in numerical studies appear to be not consistent with the CFT with SO5 symmetry.
So is that the state of the art now?
I don't know. Maybe Anders, Marx.
I think there is even a more serious problem that from the most recent correlation length exponent mu, even without SO5 symmetry, there seems to that you need another element operator.
Right, but in fact we have identified such an operator, so that may maybe the way out, and then in fact it would be the multi-critical point if that is correct. So who knows? But at least we have one case where we have seen such another relevant field. And then I guess the bootstrap bound would not be a problem anymore.
Okay. So yeah. Okay, so let me review this proposal in the easy plane case. So, basically, I will motivate this theory from dual vortex perspective. So, for easy plane case, on the square lattice, nihil antiferromagnet can be rotated into a ferromagnet, and the ferromagnet is essentially the same as a superfluid of bosons with no frustration. And back in 2001, Lannert, Fish, and Santelwey tried to use the dual vortex approach to study proximate phase, more insulating phases of bosons at half filling. So the idea being that the perspective coming from vortices is non-perturbative, and things, complicated phases in the direct line, which may be more naturally seen in the dual perspective. So here, I have square lattice of bosons at half filling. Vortices reside on this dual lattice, and vortices see each boson as a source of 2 pi flux. Now, when the bosons are at half filling, these vortices see on average pi flux through the plaquette. Now, in a superfluid, vortices are gapped, and the destruction of the superfluid is when vortices condense, and they condense at the band minima. So the first thing to do is to study the band structure of these vortices, and then you solve the particle hopping with pi flux. You find that actually there are 2 energetically equivalent band minima, so you have actually 2 low energy vortex fields to follow if you want the theory, or if you want to understand the proliferation of vortices.
Could you repeat again? I don't think I understand the model. So what is the model?
So original model is bosons hopping on square lattice with no frustration, so they can go easily into k equals 0 superfluid state. And they are at half filling, so on average 1/2 boson per site. If you have 1 boson per site, there is a very easy Mott insulator, which is translationally invariant, just 1. But when you have half integer, you have more choices for Mott insulators. So now the vortices, so the theory of vortices is that it's a gauge theory. So these vortices are quantum particles, and they see the fluctuation of the original boson density we see as basically a gauge field. Now we have 2 species of vortices, psi1 and psi2, and there is still a gauge field encoding the coarse-grained fluctuation in the density of vortices, and so this first part is basically has 2 complex fields coupled to a non-compact U1 gauge field. So that coarse-grained density of vortices is encoded as flux of a non-compact U1 gauge field. But physically, actually, there is only 1 vortex field. Just this theory by itself has higher symmetry than the physical problem. And when you study things carefully, actually you realize that there is indeed this tunneling term, so where 4 vortices of type 1 convert to 4 vortices of the other type, and that's the very first, the lowest order term which is allowed in this theory when you analyze this theory. And then, so the superfluid is where the vortices are gapped. Now destruction of the superfluid is where the vortice is condensed, so the mass for the vortex field goes to 0, and then the specific condensation pattern then depends on the details of your quartic terms, and when this interaction between these vortex fields is not too large, you want to condense both vortices simultaneously, both of these species, and then the further details of the condensation are then settled by the tunneling term, and depending on the sign of the tunneling term, when you analyze, you will either end up in a columnar. For one sign, you end up in the columnar valence bond solid phase, and for the other sign, you end up in the VBS valence bond solid phase. Okay, so these are pictures from this original paper.
What is plotted here in terms of psi 1 and psi 2?
So here this is already some, so there is some specific pattern of condensation, the expectation values of this field, psi 1 and psi 2, selected by basically minimization of this energy. And what is the way we analyzed it, we just converted it to some observable, like vortex hopping energy. And from that observable, you can see that there is I think this is probably that there is higher energy on these links than on all other links, and you stay at this and you realize that this is the valence bond solved. I think this is probably the thin line is probably the vortex lattice, and in this pattern probably this energy is larger than all other energies, and then you conclude, oh, that means that in the original spin model this has large energy. That's the pattern of translational symmetry breaking. And or in the other pattern of symmetry breaking, you analyze what it corresponds to in the original language, and you conclude it's a plaquette valence bond solid.
But the effective theory you wrote here does not break translational symmetry.
But these fields, no, these fields psi 1 and psi 2, they are at different momenta. So when
right.
you and then when you so basically there are for each of these there are you find 4 ground states, 4 minima of this energy, and then you 4 equivalent minima, and you analyze, pick one, analyze what it means in terms of some observables, and you conclude, oh, that's this valence bond solid.
I see. So the pictures here are not in terms of the effective theory, but in terms of the original theory.
So I think the pictures, the thin lines are probably observable in the vortex theory on the lattice, and then you conclude, oh, this pattern, these are some like some energy terms. So that should be energy terms in the original theory too, and you analyze, oh, it's probably corresponding to this columnar order. I think that's how we, if interpreted physically, what this means in the original theory. Okay. So now to the DQCP. If you start with this theory, so now you have 2 bosonic fields, and just run a duality again. So do vortices in the low energy vortex field. So you can do this. If you ignore this tunneling term, okay, if you just forget for a moment about this, it turns out that the dual to this theory has qualitatively the same structure. It has two fields, two complex fields, Z1 and Z2, and they are coupled to a non-compact gauge field. Okay, so that's the if you ignore the quarter. You can keep track what is happening now. Restore these tunneling terms, and what that corresponds under the duality is that actually in this degrees of freedom you have to allow quadrupled monopoles in the gauge field. So that when you carry out this duality, you can actually see this explicitly. And now, what is the interpretation of these fields? Actually, the meaning of them is that they are parton fields fractionalizing the magnetic order parameter. You can arrive at exactly the same theory if you start with formally writing S plus as Z1 star Z2, basically CP1 representation of the Néel order parameter. And you know that when you use this parton representation, it always comes with an emergent compact gauge field, and then these early works of Haldane and Sajdev and Reed, they analyzed this and they showed that actually there is destructive interference for monopoles of strength 1, 2, and 3, but for quadrupled monopoles there is no such destructive interference, and then this is the structure of this field. And this original proposal of deconfined criticality was conjecture that these quadrupled monopoles are irrelevant at the phase transition, and that the phase transition is described by this NCCP1 model. And in the easy plane case, you can motivate this from vortices, but you can also motivate it from partons. In the SU2 case, you have you can motivate this structure from the parton field.
Well, there is a C4 also in the previous description, so it seems kind of term.
Sorry?
The fact that only the first tunneling term in the previous slide was of 8's order. The symmetry is U1 times C4. There is a U1 monopole times C4 from the...
So this theory has no monopoles allowed.
No, I'm saying the symmetry of this theory.
Yeah.
Are U1 topological from the monopole times C4? And that's also the symmetry of the next slide.
Because they are related by duality.
I don't know if it's really duality or whatever, but yeah.
There is a formal duality which one can carry out on a lattice where the dual theory really has exactly the structure. So they are really related. Yeah. Okay.
So is there an explicit duality in the lattice?
Yes. One can carry out this. There is this dual structure for the easy plane NCCP1, and then in that one can also follow what happens if you have more than easy plane NCCP1, if you have these tunneling terms.
Is there an exact Z2 switching Psi1 and Psi2?
Yes, there is. It's that energetic. Basically, it's part of the vortex PSG, the projective symmetry group for this vortex band structure. Okay, what's the current status of this easy plane DQCP? I already discussed current status very briefly of VSU2. For the easy plane, actually, even already early studies were suggesting that a weak first order transition in this case.
Can you explain just because I never understood why do we care if it's second order or not?
Well, if
some experiment or what?
yeah,
The interesting thing about this model for me was that there is no gapped phase, trivial gapped phase. This is true.
well, but also it would be interesting if there is a critical theory, and strictly speaking, these scenarios of irrelevance of monopoles, that's only at the critical point.
Okay.
So.
If there's a second order transition, there's also an interesting CFT.
Yeah.
I just wondered.
I have another.
So, yeah.
I have another question which is maybe obvious to everybody who's thinking about this, but it's related to David's mentioning that Landau does not prohibit two second order transitions with a gapped phase in between. But this system actually has an anomaly which prohibits that gapped phase. Can you
No,
think
but
of this?
Landau would have coexistence of all the parameters.
Right.
And then basically each transition would be just onset of one order parameter, and the other you would ignore as a just background.
I mean, but what I wanted to say is that generically you can think of deformation of a Landau paradigm system from going from first order to fine-tune second order to two second orders, right?
Yeah.
With a gap in between.
Yeah.
But this system actually prohibits that gapped phase. So you could tune so that order parameters go to zero, but then if you overtune, they will still.
But I think the coexistence of two order parameters the system does not prohibit. Is it?
No, it doesn't prohibit.
Yeah.
The anomaly doesn't prohibit that, but I'm
Yeah.
saying that it's still. I think there's reason to expect that there's always a second order transition for some generic values of some generic Hamiltonians, because for systems which don't have a mixed anomaly, the second order is fine-tuned. But here you can overtune, you can never open up that gap phase. So even if in particular systems we find first order, we still would expect that some deformation of those systems, not fine-tuned deformations, would result in second order transition. Do people?
Max will probably.
Am I making myself clear or no? Okay, then maybe we can chat later. Okay.
Well, just one comment. I mean, numerically we're looking for such cases, right? We take these models that seem to have, very close to continuous transitions, and then we deform them, and they can become more strongly continuous, and then strongly first order. I mean, and then we can also see if some other phases can open up, and it seems that should be the case. So we don't seem to see like at least clear-cut, line of critical points. We don't seem to see that, which is what you are saying that should exist, right?
I would naively think that there should be that. But,
which of course was the original scenario. Right?
Well, yeah, the Landau scenario is you have order parameter 0 on one side, non-zero on the other side. And the non-Landau aspect here is that you have two order parameters, and simultaneously one is vanishing and the other is onsetting. And generically, rather than in a fine-tuned. Kind of generic Landau with two order parameters is that one will set in and one is non-zero, then the other sets in, and then the first one vanishes. So that would be the generic Landau scenario with two order parameters. So I think this was the possibility that somehow these things in the quantum system happen at the same time. Yeah, but yeah, Landau thinking is much more naive.
But so related question, so even if it would turn out that it's multi-critical, can that multi-critical point be beyond Landau in the sense that this deconfinement, description of the deconfined fields would still be necessary at that point, which would be still non-Landau, right?
There is soft anomaly in this theory. It cannot be Landau.
Right.
Yeah.
But then, such a point would still be very interesting then, I guess. That's what you're
It's
saying.
just a fixed point with soft anomaly. There are millions of those. I'm not sure about focus points.
So you say non-Landau is no big deal.
I mean, this, fixed points with soft anomalies exist already for 4 decades. I'm not sure exactly why this particular example is so important. Yeah, there's some peculiarities that it only has bosons, and other fixed points with soft anomalies have always confirmed.
But I don't think such points are very commonly observed in nature or in lattice models. Maybe you can hook up 1,000 field theories, but that's maybe different from actually having a complete lattice model or a material. But
yeah, he historically, I guess, when people first realized like quantum to classical mapping, people were saying, oh, everything is stat Mach. But then people realize, oh, actually there is more to quantum systems. There are Berry phases and so on. So I think the fact that it's quadruple monopoles is, again, much more richness in quantum systems. Maybe from the point of view of quantum field theory, these are not as exotic or unusual. Okay, despite whether it's continuous or not, there were other interesting developments of whether theory should be kind of recently better understanding of the interplay of symmetries and dualities, relation to other theories, but all of these kind of beautiful stories are complicated by the fact that all these formulations are strongly coupled field theories, and we do not really know what happens in the infrared for them. Maybe now with Bootstrap one can exclude some of them, and also numerical studies are challenging when you have very weak first-order behavior. So that was our motivation to look for instances of these in one-dimensional system. And this is now, so a crude idea of the wedge system to study in one dimension was like this. So this this Lannert-Fischer-Sentil analysis was analyzing unusual condensation patterns of vortices in 2D systems with U1 symmetry. Now in 2D, vortices are quantum particles, and that's where, for particles is where we have best intuition for fields. And now in 1D, when you have a system with a discrete symmetry, where defects in that order parameter are domain walls, and we are quantum particles. And then kind of very crudely idea was maybe there are some versions of Ising model where you will have some more complicated dispersion of domain walls, and analyzing the condensation pattern with that dispersion will give you some interesting phase, maybe like some lattice symmetry breaking and some theory of the transition. And one important insight here is that just Ising, quantum Ising model with only one Ising symmetry is actually not enough. For this, you need more symmetries, and crudely speaking, you need something which is analogous to what was Hall feeling for bosons.
Why is one single one enough? I need to understand.
it's then hard to have, you can get more complicated if you introduce like second neighbor interactions, more complicated band structure for the domain walls, but it's very hard to pin the momenta of this band structure. And
you could have a true phenomenon with just a single Z2. So there are such models with persistent order, also in 1+1.
yeah. Yeah, so I am thinking in like more concrete terms. So for me, some lattice model and thinking in terms of defects in the order parameters were my motivation and my thinking about this. I'm not sure. Like I was trying this for some time back in 2006 or 2005, and I could not get to work with did not come up with any Ising version where something similar to Lannert, Sandfield, Fisher worked. But if you add talking with Shenhan, he immediately suggested that actually one needs to enlarge the symmetry, and his motivation was actually one needs a symmetry with LSM theorem. But yeah. So now here is the specific. So let me write down specific model, and then that will fix also the symmetries that we have. So here we have Ising. So we have spin-1 half chain with two Z2 symmetries. So we have basically sigma x interaction with some coupling, and sigma z interaction with another coupling. So sigma z interaction familiar in quantumizing model, and the symmetry, it's symmetric under this gx, which is product of all sigma x's. Now with sigma x interaction is of course symmetric under this, and it's symmetric. It has a single transverse field that would be all. But if you have two product of sigma x's, there is also Z2 symmetry of product of all sigma z's. Okay, so that's the two Ising symmetries, and of course this is we want one of the phase to be lattice symmetry broken phase, so this is a translationally invariant Hamiltonian translation is another symmetry. And just focusing on this nearest neighbor terms, if Jz dominates, sigma z obtains an expectation value, you break Gx symmetry, while if Jx dominates, sigma x obtains an expectation value, and you break the other symmetry. And I will call where sigma z obtains an expectation value z ferromagnet, loosely speaking, and then sigma x obtains an expectation value when it's x. And here, and so that's the symmetry point. And then now to induce a VBS phase, we can add second neighbor terms with the same symmetry. So the simplest would be second neighbor sigma x, and sigma z. And we actually know that for spin half, Heisenberg model with second neighbor interaction has a valence bond solid phase at intermediate second neighbor coupling. And the easy plane spin half model also has the same VBS phase. So we expect that the first term, when it's dominant, we will have a symmetry break. And then one can anticipate the phase diagram like this. So I will always choose Jz to dominate. So this the magnetically ordered phase will be with ZFM for small k, and then at large k it will give way to valence bond solid, and we hope to realize a continuous transition between these two, but there is a direct transition and it's continuous. So there are actually, in 1D we have so many tools, there are several different ways to approach this transition. The one that I will present is not necessarily the simplest way, but it's the way which parallels the DQCP story most closely. So you will see the same structures, and in 1D it's kind of much easier to check all the math and see that this is indeed like some of the things which looked I just stated in 2D look very unfamiliar in 1D, which they are much easier to check. So that's the approach which I will pursue. So thinking in domain, in terms of domain walls, I will need duality for the Ising symmetry. So let me quickly review this because I will need to add one wrinkle to this duality. So let's consider just quantumizing chain, so sigma z plus transverse field sigma x. And the naive duality that everyone in this room knows, we just say define mu x as sigma z, and then the conjugate mu z variable work out such that mu z is the sigma x. And to express mu z in terms of sigmas, we usually say, oh, we run a string from one end to string of sigma x. So it's some non-local transformation. Okay. And then under this duality, what was interaction, z interaction becomes transverse field, and what was transverse field becomes interaction of these degrees of freedom. And this is very nice and fine for bulk properties. For example, you can immediately suspect that J equal H is special and likely at the critical point because this theory is then exactly self-dual. But this formulation actually is known to be not exact, but there are subtleties when you try to study it on finite systems, like capturing the ground state degeneracy in which phase. All of this has long history, and people know how to recover this with enough care, but one needs to be aware of this, and particularly if you want to keep track of your symmetries under this transformation. Okay. So, for example, this field, ordering field, is a very non-local expression in terms of these dual variables. Okay. So now to achieve this, so one formulation that allows keeping track of symmetry is works very nicely on for a finite chain with periodic boundary condition, is to view the dual theory as actually a gauge theory. So you can make this duality transformation exact if you add a new field, which is a gauge field, and this replace the mu z by proper gauge invariant term, mu z, rho z, mu z. So this gauge field resides between the dual lattice sides, so it actually resides, you can think of it as residing on the original lattice. And you may think I added some new degrees of freedom, and many of them, but actually in one dimension, gauge theory is a very small object. For example, if you do not have, so you need to modify, so it's a gauge field, so you also add a Gauss law constraint. So this is Z2 version of constraint. So it becomes a matter gauge theory, and the statement that gauge theory is a very small object, you can immediately see, if you just think what is pure gauge theory in one dimension where there is no matter, this is just one. Actually, for any system size the full Hilbert space is just two-dimensional. So you really just add very little, but just enough to be able to capture the symmetry properties that are missing under this naive approach. Okay, and so the precise statement is that this now gauge theory, Ising gauge theory, is actually exactly equivalent to the original Ising model. And the way you can establish this is almost trivial. You do not need to run any strings. You just do identification. You have 2-to-L dimensional Hilbert space for the original spin model, and you just count the Hilbert space size for this gauge theory with this constraint, and at the level of basis states there is one-to-one correspondence, and then you just match the action of operators in on these basis states, and these are really identical. Okay, so now in under this duality, the original Ising symmetry is actually encoded as flux conservation of this dual gauge. Basically, this commutes with the Hamiltonian, so this product of rho z's commutes with the Hamiltonian, and that means that you are not allowed to have a single rho x in this Hamiltonian, and I will refer to this. So this single rho x would change the flux. It would like insert a Wison, and I will refer to this that we are not allowed to have Wison or instanton events in this gauge theory. So this is analogous that in the dual vortex theory for bosons in 2D, the dual gauge field is non-compact. You are not allowed to add monopoles in the field. Okay.
Can I ask a question? In the continuum, this is just bosonization. Is that maybe my voice should have gone up at the end?
I think you can call it whatever. Yeah, this is what the Kramer-Svanja duality is, and I just want to make it more precise so that one can keep track of all symmetries. And for PBC chain, this is really now exact. And now the original sigma z field is actually this rho x. In the original, when you have Ising symmetry, you cannot add sigma z to the Hamiltonian. In this gauge theory, you say there is flux conservation, you cannot add rho x to the Hamiltonian. Okay? And this also, because it's exact, it should capture all global aspects like ferromagnetic phase when J dominates over H. There is twofold ground state degeneracy, and the way it's captured here and not captured in the naive way, J dominates. It's a paramagnet. You would say there is only one ground state, but actually there is still gauge field left. And when the matter is gapped, there is no distinction between the two flux centers, or it's exponentially small in system size. So that's how it's captured. Okay. So now. I want to apply this to our spin 1/2 model, so develop thinking in terms of in terms of domain or defects. And one can run this, so I copied this model with nearest neighbor and second neighbor interactions, and I copied the duality transformation, and I just can carry this out. So sigma z, just like in the Ising model, is mu x. Now sigma x, a single sigma x is a product of nearest neighbor mu z. Product of nearest neighbor sigma x is actually product of second neighbor mu z. Okay, so that's how Jx terms looks. Now, if you forget about this dual gauge field for a moment, under this duality, these Jx and Jz terms look like you actually have two decoupled Z2 systems because there is only second neighbor coupling. Okay, so there are two sublattices on the dual lattice, and you have separate Z2 on each of these lattices. Okay, and when you add with K2 terms, you see, for example, this second neighbor becomes actually a coupling between transverse fields on V2 or on sublattice 1 and sublattice 2. So you basically these terms actually and actually any term which you can add, which are symmetric under the original, they will not change the fact that these two, there are two independent Z2s, but they will only introduce energy-energy couplings between these two Z2 fields. Okay? And I can write very crude continuum theory for these two separate Z2 fields that there is for the two sublattices, and they should be symmetric in the two flavors because really they are related by a translation symmetry, and I can analyze the destruction of the order when these domain walls start condensing. So if these domain walls are gapped, that's the original ferromagnetic phase. If they start condensing, the original ferromagnetic phase is destroyed and something else emerges. And what is the phase that emerges depends on the details of the quartic terms. So if this coupling, energy-energy coupling between the two is small enough, then you want to condense both domain walls, and if you analyze what that phase is, it's actually you restore the GX symmetry and break GZ symmetry. You get an expectation value of sigma x. Well, if you condense one domain wall while the other is gapped, or vice versa, these are two energetically equivalent possibilities, you can immediately anticipate this will be translational symmetry breaking because you condense something on one sublattice and not on the other. Okay, and when you analyze this, this is the valence bond solid phase. Okay.
Sorry, quick question.
Yeah.
Is my intuition correct that if you put the couplings Jx and Jz and K,
Yeah.
equal, you will have a U1 symmetry.
Yes.
And there will be a transition from Z2 broken. You will have U1 cross Z2.
Yeah, you will have a quasi-long range order phase transition to valence bond solid phase.
And at the transition, there should be an SU2 Westermann-Witten phase, the enhancement to SO3. So actually SU2 cross SU2 in the symmetries. Was that studied? I think based on the anomalies, that's what I would expect.
I think so. Yes. Yeah. This transition is. I think it has enhanced.
Yeah. Because this is kind of. I guess this could be obtained by a reduction of JQ or something like that.
So
reduction of symmetry.
I can tell more. One way to understand this transition is to start with theory for this. Okay. The problem is when you analyze it, it's actually you have two. So first of all, in quasi-long range ordered phase is immediately unstable the moment you break the symmetry from U1. That's okay. Now here, what happens is that you can write down the theory, and you have two cosines containing conjugate variables, and they are one. They have to be tuned where they are both simultaneously relevant. Both marginal at the transition, and then you have to decide what is the fate of that field. And you may suspect that that theory, it's theory where you have cos theta, maybe some multiple of theta plus cos some multiple of phi, and these multiples are such, and the Gaussian part is such that they are marginal. And then you have to decide what is the fate of that theory, and you may suspect that it will be strictly marginal and it will give rise to continuously varying exponents, and that's indeed what happens. But it's actually, to establish that that's true, it's a non-perturbative argument. I do not think there is a the way this is established is actually quite non-trivial.
So are you talking now about the transition in your model?
Yeah. If you try to understand this transition, starting with these fields.
Yeah. So I would expect that to be a compact scalar, which I think you call on the transition in this model. There would be a compact scalar CFT, which indeed does have exactly marginal.
That's what the transition turns out to be, and
that's what you see.
Yes, yeah. The theory for the transition is actually in the end very simple. The structure of the theory. Okay, I actually see that I am way behind in time, but I said we can understand the phases from these two species of domain walls, and now in these variables, so Ferro is this domain walls are gap. VBS is this is condensation pattern where one is condensed, the other is not. It's actually more convenient to work with different domain wall fields where I will take a symmetric and anti-symmetric condensation of these mu A and mu B. And if you think about this, it's like the symmetric combination now is translationally invariant. It's like zero momentum domain wall, and the anti-symmetric combination is like pi momentum domain wall. And indeed, if you think, if you just solve second problem which has only second neighbor hopping, you have two equivalent band minima, 0 and pi, and that's these domain walls. And translation of you can easily translate what I described in terms of these lattice domain walls mu A and mu B to these momentum domain walls 0 and pi momentum, and more specifically these possibilities both condense or one condenses, the other does not. We are swapped under this transformation. So VBS phase in this case is understood as simultaneous condensation of both k equals 0 and k equal pi domain walls. And one can actually write down VBS order parameter is basically product of these Ising fields describing these domain walls. Yeah.
One of them is gauged and one of them is?
Both are gauged. Both are gauged. So now the ferromagnet to VBS transition is you have crudely two Ising systems where there is a simultaneous condensation of both Ising fields happening, and already at this point you can suspect this will be this is structure of Ashkin-Teller model, and the Ashkin-Teller model for this transition has a line of critical line with continuously varying exponents. Now here, if one wants to really understand all symmetry properties correctly, one has to remember that these domain wall Ising variables are actually gauged. So this is gauged Ashkin-Teller, okay? And to also. Yeah.
So, in terms of the critical exponents and so on, is the gauge as Ashkin-Teller different?
No, but the identification of the fields, you really have to keep track of this, the meaning of the fields. Yeah.
But could there be some difference in terms of?
No, because it's really the adding gauge theory in bulk is very little. Not like there is, it's really order one for the full system. Okay. So so now, if one wants to be really careful about symmetries, so how do I, like in continuum, how do I include the Z2 gauge field? It's a little bit challenging. So the way we did this is actually we relatticized this. We put these 0 and pi momentum domain walls back onto a lattice. You can think of cross-graining and forming wave packets and putting them, relatticizing this again. And in the structure of the theory, and you can put them on the same lattice side too. And the way this lattice side where I will put them back, I will label as half integer. So it's, strictly speaking, there should be some cross-grain lattice, but I will label it as if they are in between of the original lattice sides, okay? So when this is the structure, so you have two species, mu plus, mu minus, you have to keep the gauge field to account for global aspects, and when you relaticize, actually you know there is only one physical domain wall, but they differ by momentum, but on the lattice you can account for that. You can convert from one domain wall to the other if you borrow momentum pi from the lattice. So this basically this is the relaticized version which has the same qualitatively the same physics in it.
So what does this word relaticize mean?
Well, you know, for this to be meaningful, I had to go to the continuum, to be talking about zero and pi momentum fields. I had to go to a continuum, and how do I? But now I want to go back to lattice, to work on a lattice. So that's basically the statement is that now this theory is not identical to the domain wall theory I had, which was exact rewriting, but it's qualitatively the same. Okay. It has the same field content, and all the symmetries can be completely encoded in this field content. Okay, and this is analogous to like in this quartic tunneling of from one vortex species to the other vortex species, very strong. And
you could do it all in continuum too. I mean,
yeah, but I wanted so next I want to do domain walls in the domain walls, and I want to do it carefully, and in continuum it's more challenging, so I put it back on the lattice. Okay. So now we have you can think I just wrote down some new lattice gauge theory with two Z2 matter fields and one Z2 gauge field, and I just postulated it, and and what I want to see is that physics content of this is qualitatively the same as the previous.
I think the main point should be that the domain wall has the right anomaly inflow. Actually, this is probably.
Yeah, this is.
And the details shouldn't matter.
Yeah, that's basically my StatMag background tells that different lattice models with the same symmetry should have the same qualitative physics. I just, my mind works on lattice, your mind works in continuum.
No, I love
so
lattice.
you
I love lattice.
yeah. So like your question about the duality, I see that I'm really short on time behind what I was planning to. So let me. I will be very telegraphic now. Basically, like you had a question that can one show these U1 dualities on the lattice, and I said yes, one can. And here there will be lattice versions of in the Eisenkins duality. Okay? So now, so this is theory in terms of domain walls, and again, one can understand. Well, one could stop here and one could declare this is Ashkin-Tell and we are done. And crudely one would be already okay, but again, the way one understands Ashkin-Tell, it's not in terms of these fields. There is a very non-trivial transformation to right degrees of freedom in the description of the Ashkin-Tell. And to we wanted to be very accurate, and that's why we relate this. Okay? And here, again, the transition is both with domain walls, where ferromagnet is where these domain J is very large, with domain walls again. Transition is where both of them condense simultaneously, and this is the order parameter. Okay? And the original sigma z is encoded in the flux. Now I will run the same thing, domain walls in with low energy domain walls. To duality. You can carry this out. I will not go through any steps. I will just state this Z2 Isengage theory on the lattice is mathematically equivalent to a new Isengage theory on the lattice. The content of this new Isengage theory, it also has two Ising matter fields, and it has one Isengage field, where these matter fields and gauge fields reside are swapped compared to this, and the matter field actually allows allows Visons like this. Okay, and it allows it doesn't have flux conservation. Basically, you can change the flux.
So you don't impose flatness.
Yeah. Here, this theory, you are not allowed to have rho x change flux. Exact rewriting of this theory, you have the other side of the duality. You are allowed to change flux dynamically.
So how do the symmetries work?
One can work this out completely. The statement of the duality is again 100% exact on PDC, that it's a one-to-one correspondence between Hilbert spaces and one-to-one correspondence between the action of the operators. Okay, and then you can actually work out what the symmetries of how the symmetries are realized. Okay, and this theory, so this is analogous to the dual of the vortex theory. So here, one had the tunneling in the vortex theory corresponded to allowing quadrupled monopoles in the dual theory. This is basically allowing Visons in the dual theory. Okay, this term. So, and again, actually, the proof of equivalence is pretty elementary. Just match the basis for the two-gauge theory with the physical states and match the operator.
The original one, the only symmetry I see is the Z2 symmetry, which is the conservation of the sum of rho. Right, rho is the
there are two Z2. There is also the interchange symmetry between the two species.
Okay, good. So what does that map to here? There's only one species or two?
There are two species.
Okay, sigma is two.
Yeah.
And it's still in the exchange symmetry, that one? Here. So there are two Z2, you're right, here. And what are the two Z2s here? Because it looks like this, am I wrong? It looks like the same model except there's no flatness condition. And since the flatness had a Z2 symmetry here, implied a Z2 symmetry here, I'm confused how even the number of symmetries is the same.
There is one obvious swap of the two flavors.
In both, right?
Yeah,
Both
and
if it's not important, maybe we can discuss later.
yeah, there is another Z2 symmetry. So sorry. It's actually, there is a symmetry that basically changes sign of one flavor but not
And that's
the other.
not in the original thing, right?
And
The secret,
it's not in the
yeah,
original.
because-
But basically, what is the meaning of this? So I formally obtained it by this formal duality. And what is the meaning of this? Actually, one can arrive at exactly the same theory by formal fractionalization of the sigma z. There is basically one can cook up a fractionalization where this will be some gauge theory. I enlarge the Hilbert space, but then I will select specific subspace to match. So some gauge theory, physical subspace will match the spin subspace. There is a specific choice of PSG for this fractionalization that will give exactly this, for the effective theory, will give exactly this structure with, when you fractionalize, you have to allow where there is emergent gauge field, where it should have instantaneous events, but the way we are allowed has exactly this structure. So one can really interpret this as effective gauge theory for fractionalizing the magnetic order parameter. Okay, and so here is just the summary where basically we have two theories. One is in terms of domain walls, and this theory, these fields are basically fractionalizing the VBS order parameter. But if you look at it this way, and the ferromagnetic order parameter is encoded as a Wison of the gauge field, and the parton theory, it's the opposite. You fractionalize the ferromagnetic order parameter, and VBS is encoded as a Wison of the gauge field. Okay? And the transitions are basically from here you condense both mu from ferromagnet to VBS, or VBS to ferromagnet, you condense both ways. And the analog of the assumption of deconfined criticality is where if this gamma term is irrelevant at the transition, then you could drop it, and then actually qualitatively the structure of the theory is the same as two Ising models with energy-energy coupling. And that's the known self-duality of the Ashkin-Teller. Okay? So now, I said that actually I could have written this field theory long ago, but where we expect the transition to the Ashkin-Teller-like, and the theory for the Ashkin-Teller, the way we understand it, and it's continuously varying critical exponents, is that it's like C equal 1 theory, where there is field phi tilde and conjugate to it, and there is one Lattinger parameter, and we are in the regime where this there is one allowed cosine, and we are in the regime where this cosine is relevant. So this is not a stable gapless phase, but what is happening, the transition is where this cosine, the coupling of this cosine changes sign. So at the transition, the coupling is 0, and the relevant direction, the thermal direction for the transition is this relevant cosine. Okay, so that's how one understands it. But if we want to, the way these variables are arrived at is very non-trivial from, so from the Ising degrees of freedom and Ising-Ashkin-Teller, it's actually like a two-step, very non-trivial duality. Yes?
I understand the comment about the sign. If you just shift theta by, I don't know, pi over 2, flip sign.
So this is basically the meaning of theta is fixed by identification, like what other parameter it represents.
Flipping the sign of lambda seems to be pretty innocuous thing to do.
But you see, once you fixed what the representation of your microscopic degrees of freedom in this, that fixes for you the sign. So there is some choice when you derive this microscopically, like Latinger liquid theory. When you derive microscopically, there is some assignment. What is your one order parameter and what is your other? And one order parameter may be cos theta and the other is sine theta, and then you fixed the meaning. Yes.
Will you tell us what is the correspondence with the microscopic?
Yes. So let me. So I will skip. I wanted to spend to say that actually with these exact dualities we were able to arrive at the correct variables for our model microscopically. But I will skip and will go straight to answer Max's question. So this is the final theory, okay? Or final theory for the transition. And these are the identification of the microscopic order parameters. So specifically, the ferromagnetic order parameter is represented as sine of this theta. The VBS order parameter is represented as cos of theta. Actually, the full theory, so if I had only cos theta, I would have U1 symmetry. So the full theory has specific cos theta and specific cos phi. But it is in the regime, this transition is in the regime where the phi, cos phi is irrelevant and cos theta is relevant. And then the transition is driven by change of sign of the lambda of the cos theta field.
But I don't understand this. How can that be? I mean, the sign really does not matter. You would have the same phase on both sides. I think what it means.
Well, the analysis does not matter, but the identification. You see here, once when one derives it, one makes some choices.
That's not the issue, but I would expect that the transition happens when one of them becomes irrelevant, the other one becomes relevant.
No, that's not. No. That transition is a strongly coupled theory that I said I could have it's a different, the transition I'm interested in is not the transition where one becomes relevant and where we are swapping the relevance irrelevance. That transition is, you cannot understand it perturbatively in these variables. You would need to actually do to understand that that there is actually in some sense strict marginal, you cannot understand in these variables other than just saying, look, we have the same scaling dimension and it happens to be precisely 2. So most likely the outcome is that they will keep balancing each other and you will be you have continuously varying exponents. But that you would not be, these variables would not be good variables for that transition. Okay? Now,
language is not doing the dual shift symmetry whatsoever. It's using charge computation and the momentum you want. So that's why phi equals 0 is kind of...
Yeah, the transition in this theory that I'm interested in is where I am in the regime where this can be dropped off and is irrelevant, okay, as far as the transition is concerned. It's relevant if I want to understand the phase. But this thing is relevant, but is tuned across 0. Tuned from positive to negative. And the two phases are, one is positive lambda and one is negative lambda. And the meaning of these phases is encoded how the original order parameters are represented in terms of these fields. So this is where...
I thought one is theta.
No. It's the same theta which enters for this. Okay? And like I skipped multiple slides, but basically we can actually that non-trivial steps that I was saying, how one understands how Ashkin-Teller maps to this type of transition, lambda changing sign. There are two dualities, two-step duality to arrive at these variables. It turns out that for the gauged Ashkin-Teller, all of that can be made 100% exact, keeping track of all symmetries. Okay, and that's the final story for the transition. So basically, and at this point, actually, how I arrived at this transition, you can almost forget. Actually, there is a way to arrive at this transition without ever fractionalizing anything. It's somewhat non-trivial to guess, to see why I should be arriving at that way, but you can actually arrive at this without fractionalizing anything. But what I want to bring out here is that these original domain wall or parton variables are not variables that are convenient for understanding actually this second order transition. They may be good, they may be starting point, motivating point, but the way we understand the transition are actually non-trivial variables. In some sense, these variables, so if one follows through the steps, which I skipped, they are like some different parton variables where actually partons are gapped in both phases, but undergo some SPT to trivial transition. And the order parameters are always encoded in the instantones of the gauge theory. So that these type of variables turned out to be the nice variables where we really know and understand the theory of the transition. So that's the theory, and I will just quickly wrap up the first part. And we know everything about this theory. All scaling dimensions of ferromagnet and BBS order parameter have the same scaling dimension. We know all observables by scaling dimension. But we wanted to see also that the specific lattice model, there is lattice model by this is realized, and actually the very model that I wrote down, in this model we study it. So it's a frustrated model, but we can study it using DMRG in one dimension. And this is actually the phase diagram that we find. And we indeed find a large range of direct transition between the two phases, and the transition is continuous. It has continuously varying critical indices, as you expect, because there is one Lattinger parameter, and everything is working out very beautifully. The VDS and the ferromagnetic order parameter have the same scaling dimension, and because there is really only one parameter in the theory, all exponents are related, and we can check these relations. So there are specific relations. So now this is walking along this phase boundary and studying the phase transition at various points and checking if the relations that we expect are satisfied. So here we wrote these relations as product of some exponents equal to 1. So the exponents vary, but these relations are all satisfied, and that's basically the story for this Ising criticality. And again, one possible lesson from this is that in the end, the good variables for the description of the transition are not domain wall or parton variables for the ferromagnetic. They are actually some different variables, as I mentioned. There are different ways of viewing it. One is to view them as partons which are gapped in both phases but undergo an SPT transition. And we do not know such description for 2D DQCPs, and maybe it doesn't work for 2D DQCPs, but maybe some other interesting critical points can be arrived at via something like this. So that's the Ising story, and I am already 1.5 hours in. The second story should be shorter.
But I mean, I don't want you to rush through,
okay.
through things. So I mean, you decide what you want to do. But I mean, 2 hours is quite long, so I wouldn't go over time.
Okay.
If
yeah.
that's possible.
Yeah. So maybe a 5-minute break here, and I'll try to be. Yeah. Of course, the questions are, of course, great, but I clearly did not account for them.
2 hours is not that long. People
Can I
think
still ask one question about this part? So in your phase diagram from DMRD, you had some other phases there too. So can you?
Yeah, basically there are actually 2 different VBS which have some subtle distinction between them, but precise distinction with the presence of these Z2 symmetries. Actually, we also find a region of coexistence between ferromagnet and VBS, which can be understood within the same field theory. Actually, that region is where precisely the endpoint of that region is, I think, actually, yeah, I think this is where basically the Latinger parameter exits this regime.
The reason I ask is that we had this work a long time ago on an extended Hubbard model where we saw basically this kind of transition, but we didn't understand it like that. But there we had another phase too, which is like the critical Heisenberg phase. So is one of your phases also like that? It's a gapless algebraic phase?
No. Here, these are all. This phase is a coexistence of ferromagnet and VBS.
So what's your XUUDP?
That's a more complicated pattern of translation symmetry breaking. It's actually. I think probably also coexistence of ferromagnet and a different translation symmetry breaking.
Can you get a critical phase in your theory?
Not in this theory.
I think this coexistent region and DQCP has a joint at a point, right?
Basically, I think where the description of the DQCP of this transition ends. So here, where this applies, where I said very specifically the regime for Latinger coupling, where this is irrelevant and this is relevant.
Yeah, I think when
and
G equals 2, right?
Yeah.
When G equals 2,
Yeah.
that's the special.
Yeah. And what happens is where this is when that theory is no longer basically that theory is no longer giving base transition, it does something else, and we actually can understand within that theory with appearance of
That's very
coexistence.
interesting, and it may connect to the 2D thing, because in the model we studied before, we did have a critical phase as well, and now you're saying that that cannot be captured by your theory, but with some added ingredient, you know, that must show up as well, and that may be relevant to the 2D case as well, right?
Yeah, maybe.
Because we have a gapless phase which also connects to, you know, to this line of critical points.
I think your model has higher symmetry, so maybe.
Yeah, well, that's true. It has.
Yeah, so for the purpose of this talk, actually, I could have just cut the phase diagram here because I really just wanted to focus on this. But I think this part we understand within the same theory also. There is.
Okay, maybe we can discuss more.
So that termination of the coexistence space, is that the point where cosine 4 theta becomes?
I think they basically yes. Formally, one becomes this becomes relevant and this becomes irrelevant.
That's just like the other end where you have the SU2 symmetry, or of U1 where you have the quite long range. You get that.
Yeah, I would need to remind myself. We had an understanding. I don't know. Yeah, so maybe 5-minute break and then the next story, which I'm also quite excited about. So, and I'll try to finish it within 2 minutes.
Last speaker was complaining that we were clapping in between the breaks because that means you're finished, but so it wasn't no. Did you stop the stream? Yeah, so just if you couldn't not go over time too much.
Okay.
Because I think people
yeah.
are tired and they may have questions also.
Yeah.
So
I will
just summarize.
I will try to
main points or something.
Yes. Okay.
Feel free to use the board if that will make you faster at summarizing something. I don't know.
No, I will just
flip through slides. Okay.
Yeah, I can.
Just stand here on the side.
I only saw that.
Sorry?
I mean, people are complaining, like moving around.
No. I meant like last time in the break, I said let's thank the speaker, and he said, but I'm not finished yet. So this time I didn't know whether I should invite people to clap or not.
Sorry, I clapped first.
That's okay. I think it's always good. But I mean, the point I was making, and it about the Landau paradigm. If you have a generically second order transition, first order transition. Sorry. I mean first order. So this is one symmetry is spontaneously broken, for example. And here you have G2 spontaneously broken, and it's a first order generically, but you can change some parameter and you can fine tune it to be second order, right? Landau paradigm does not prohibit that, right? So there could be a second order, and then there could be 2 second order lines with a gap phase in between. This is Landau.
Coexistence. The Landau would be coexistence.
I think coexistence is the first order line, right? Along the first order line.
Yeah. So this is first
coexistence
order
is a
line. This
second.
is coexistence.
Yeah.
Right?
But
and then you can fine tune so that it is a multi.
It's a phase.
And then
you can have
if
it
you
open as a
overtune, you
phase,
could
not-
have 2 second order transitions. But this system has an anomaly, so this phase is prohibited.
But
So I would
you
think-
could also have a tetracritical point, right? So that you can have a coexistence phase and a disordered phase.
Sorry. What do you mean? So
Okay, so
coexistence
instead of
phase-
that line here, you could have, 2 lines there as well. I mean, that's also possible.
You could have the 2 lines as well, and then, for example, you tune something, and then there's just 1 line.
Yeah.
And but the point is, you can't have something like this. So let's have one line here, and then maybe there's a critical point, whatever, and then it goes like this. But because there's a 't Hooft anomaly, there cannot be a trivially gapped phase. So actually, this multi-critical point you would expect to be generically, if you overtune, you would expect generically there. So I would think that even if you find the first order, you should still be able to deform the system so that the first order turns to second order generically for a range of parameters.
So that's what we see. I mean, that's the original DQCP scenario, right? Because, well, of course, they never said that, oh, it's always continuous, but they said that there's a generic line of,
right?
Which
but,
is what
but
they're
for
saying.
example,
now it seems like we don't see that, right?
In your JQ model,
Right.
for example, with Z2 symmetry only, SO3 and Z2, it's first order usually, right?
Well, I mean, it seems to be very weakly first order, but
Very weakly first order. But I'm saying there should be a deformation of that model where you
Right.
end up with the critical theory.
Well,
Why-
maybe.
why- Yeah, right. Generic, so very simplest case, suppose I have two order parameters, phi and psi,
You can tune the. You can.
and you just write, suppose you have Ising symmetry or U1 symmetry or something, you just write some, so there is phi squared with some number, phi to the 4, and then there is some psi squared with a different number. There is no relation between these numbers, and maybe some interaction between them.
Yeah.
You start analyzing it, and the possibilities of energetics
But
of
that
this
doesn't have a 't Hooft anomaly, so this is not going to describe this.
No, but
Yeah,
maybe
but-
let's begin with the phase diagram.
Yeah,
Yeah,
but
so
what,
that-
what I'm saying is that you
Oh, I haven't
just
quite
analyze
decided.
the
Somebody see you until
of what is happens, and the possibilities are either a transition like this, where one is dropping to 0 discontinuously and the other starts out, or the possibility is one is vanishing
Yes.
continuously, the other opens somewhere else, or another possibility is like this. So just it just minimizing
Yes.
interactions,
Yeah.
and this
So this
you,
this is my plot here, right? I mean, this is this scenarios. You have some parameter, and you could move between these scenarios. This one.
yeah,
Is
this
this
one
one
is first
here?
order.
This one is this one
Is
here, and this
coexistence.
this one. Sorry, and this one is here
Yeah.
on top, right?
Yeah.
And these could be maybe even first order in principle, but
So, I have actually a scenario which is, I think, exactly also. Let me try that. So, now it looks like maybe in the JQ model, it's more like...
we'll probably have to resume very quickly. But,
right. Well, so we think there's a, spin liquid and multi-critical point, and, this is first order. But, that's for SU2. We also know that for SU, n goes to infinity, there should be a generic critical line. So that must mean when we, increase n, if I'm right about this, it must eventually go to that.
that's right, but you're changing symmetry with that.
That's right. So
I want
don't
to
know
keep
how
symmetry fixed, right?
Right.
And there's couplings that you can add to this model,
Yeah.
and I'm saying that I would naively expect that since the point in Landau paradigm, you naively expect that there is a second order transition between two phases, but it's just a point, it's multi-critical.
Yeah.
Because of the 't Hooft anomaly, if you are able to achieve that, it's not multi-critical because it should continue being second order even if you're overtuned.
But maybe you cannot achieve this.
Maybe you cannot
Another
achieve it, but that's a
scenario
different
could be
story.
that-
From Landau paradigm, you would expect that you can achieve second order transition. So if
As
you
a
can achieve it,
multi-critical,
because
yeah.
of 't Hooft anomaly, it's not multi-critical anymore, it is a line. It doesn't end with a
Well,
point.
No,
It is continuous.
not obvious, right? Because it can just become
Again, first order.
first order or coexistence, right?
Does
But
that make
with
sense?
't
That, the,
Hooft
that,
anomaly
that, that,
means-
that is a little bit strange because
So
what would that
say
mean for the
be-
critical
between-
theory with this parameter?
I think you can do that. I actually has a paper describing this first order to second order transition. That's precisely what you are talking about.
It's all about whether you have a CFT, right, with with the right symmetry, with the right anomaly,
right.
and
And
the
the
one
relevant
relevant
direction,
deformation.
So I guess you would need a CFT where there's a marginal operator which leads you down, when one side of the marginal operator leads you down to coexistence phase, and one sign leads you up to a CFT, it's irrelevant. So that would only be true for a marginal.
Well, you can also have I guess, two CFTs, right? Where you have one CFT, and then there is a first order region, and then the endpoint of the one CFT is another CFT with a different operator content.
Maybe, yeah. Okay, the simplest scenario I can think of is that, so then it boils down to, can we find a CFT, maybe Bootstrap or something, which has the right anomalies and has the right operators, which are, and I guess that's in the end.
So the multi-critical point at least need to have two relevant operators.
Yeah, that's the definition of multi-critical point too.
I mean,
so you
one
have
side
to
you need to tune between the two phases. The other you need to tune between first order and second order.
So the multi-critical you need to tune two parameters to each one. So generic critical you just need to tune one.
Should we start? So it's 4:45.
Okay. So
can you condense 45 minutes into 50?
I will try my best. Yeah.
Okay. Good luck. Okay, I'll see if people are outside.
Okay, so.
Is it going?
Okay, so I'm actually happy that there are so many questions that it stimulate discussion. So I will be very telegraphic about this second part, and I will be happy to discuss details with anyone later. So the Ising case is, you can feel that it's maybe very special, and with also continuously varying exponents is very special to 1D. So we were hoping to find more examples of D2CP, and what we tried is to consider models with, so next thing after spin half chain is spin 1 chain, and we tried to study if something like this happens with Z3 symmetry. Okay? So here is a specific model. So this is standard clock variables, Z3 clock variables, X and Z, and the model is really an clock version of the Ising model. So we have analogous terms to sigma Z, and sigma X. A little wrinkle is that the ZZ terms are standard in clock model, Z dagger Z, but the XX terms are actually effectively putting different alternating representations on the two sublattices. And the reason this is done is, in some sense, if you put the same representation on all lattice sides, you cannot get symmetry breaking of the dimer type. To form a singlet, you need at least 3 sides. So we wanted VBS to have dimerized-like structure. Okay. So that's the GX and GZ term. So now here, actually, we do not need to add second neighbor terms to drive the VBS order. Actually, nearest neighbor terms of this type can drive a VBS transition. So this looks somewhat more complicated, but it may actually be familiar to you as this thing by itself actually has SU3 symmetry, and it corresponds to this SU3 spin chain where you have alternating free bar representations on the two sublattices. And this one is known, this nearest neighbor SU3 chain is known to have to be in the valence bond solid phase. It's an exactly solvable integrable model. It's in the VBS phase. So when we play the same game, the competition between J-term and K-term driving a transition from from ferromagnet where Z obtains an expectation value to valence bond solid where we develop translational symmetry. And this is the result of the DMRG study. Again, I mean the regime parameterized, but JZ is 1 plus delta and Jx is 1 minus delta, and delta is always positive, so we focus always on ordering the Z obtains expectation value. And here we expect ferromagnet, here we expect valence bond solid from previously known results. And numerically we find that there is a direct transition between the two, no intermediate phases show up. And the transition is apparently continuous. As far as we can push our DMRG, it looks continuous. So so here we have evidence for a continuous transition. The correlations are power law, and the dominant correlations at the transition are actually ferromagnetic order parameter or VBS order parameter, and they appear to have the same power law. And this, as far as we could push, this is the correlation length is already for the 200 lattice space. Okay, it's bounded by the bond dimension of the DMRG that we can put in, and it has nice entanglement scaling consistent with somewhat strange central charge 1.1. Okay, but up to really as far as we can push, we do not see everything looks continuous. And the critical exponents and central charge that we extract look the same along the this whole phase diagram. So that's the numerical observations, and we were very excited, of course, about this new instance of DQCP. We tried to develop field theory for this, and we did not quite succeed. I will just give kind of two field theories which are not tractable. Yes?
Sorry, but this looks good. There was a paper by Affleck and I'm blanking, help me. The SU3 spin chain and the equivalence of the, there's a generalization of Haldane conjecture for SU3 spin chains. There is a proposal.
Miller and Affleck.
Miller and Affleck and
I think in that case,
I mean,
everything is fundamental, but in this case, fundamental and fundamental.
Yeah, there is a different SU3 chain where you have free, and the thing is that the dimerized phases is trimer. It's not dimerized. Translational symmetry is trimerized because you on two sides you cannot form a singlet there. You need at least 3 sides.
Oh, sorry. Do you want really a dimerized?
Yeah. So here where the other phase is dimer. This was the choice that we wanted that.
I see. So Z3 cross Z3, you mean the
You can think
internal symmetry.
Yeah. So one theory is to start here. Think in terms of domain balls. Everything I told for the Ising, the same can be carried out with just generalization of the Ising duality. We again have this feature that there are basically domain walls which two species of the domain walls one on one sublattice and one on the other sublattice, and we only talk via energy-energy coupling. Okay, but the same feature works here. In the absence of energy-energy coupling, this point delta equals 0, k equals 0, you can think of it as tuning from z developing order parameter to x developing order parameter, and that transition we know is two decoupled Z3 models. After this, you know it after this duality. Okay, so this point in the domain involved variables, it's two decoupled Z3. We know everything about that theory. Now, in our theory, we have energy-energy coupling between these Z3. So that would be like Z3 version of Ashkin-Teller. Unfortunately, energy-energy coupling and two decoupled Z3s is relevant. So now you have also thermal and another relevant coupling. And when you analyze actually on the positive K side, it actually leads to, if you try to keep delta to 0 on the positive K side, it actually runaway flow of energy-energy is opening up the VBS phase. Okay, so that's really not a with this starting point. We can understand the onset of the phase boundary. We can predict that it onsets as cubic, but we really don't know whether at the phase boundary these two relevant, the phase boundary is obtained by these two relevant flows are balancing each other. But what is the ultimate fate, whether it will, as they balance each other, whether they flow to new fixed point, we don't really know. So we do not have a theory for this. It was accessible for Ising model because what was very marginal energy, and the result of having them was actually the line of continuously varying exponents. But we do not have, and again, analyzed by non-perturbative means. Here we do not have anything like that. Now, another starting point for possible analysis turns out that if we take Gx equal to 0, so we inverse variables on this phase diagram, delta is equal to 1. So then actually this is diagonal in your basis. This is SU3 symmetric. You can expect you actually have U1 symmetries, in fact, two U1 symmetries. So this Z dagger Z in this Gelman or generators of SU3 they are like T8, T8, T3, T3. So you have two U1 symmetries. You can write down a bosonized theory with two U1 symmetries. And so one of the, along this line, one of the Z3 symmetries is actually contained within these two U1s, while the other U1 symmetry is, the other Z3 symmetry is still an independent symmetry permuting the flavors, okay? And one can write down a bosonized theory for these two pairs of conjugate fields phi and theta. This theory is pretty constrained by symmetries. Turns out it, besides velocity, which is just scaling of time and space, there is only one parameter, one Latinger parameter. And this structure is forced upon you by the symmetries, in particular by this Z3 symmetry. And we can write down allowed cosine terms in this U1 cross U1 symmetric theory. And there is a regime where these cosine terms are irrelevant, and there is a regime where we have central charge 2 or gapless phase in this theory, but we do not find it in our numerical study, okay? We can analyze gapped phases in this theory when these cosine terms become relevant. And we do find this theory does capture the phases of our, when we analyze possible phases coming from these cosine terms. we find in one regime of this, there are two parameters. In one regime there is ferromagnet, in another, and it's proximate to VBS. There are a couple of analysis. The transition between the two phases is actually expected to be first order, because it's really a level crossing transition. Really, the two phases are represented by disjoint, distinct, discrete points of these fields in the field. Oh, one interesting aspect about this gapless phase is actually VBS and ferromagnet happen to have the same scaling dimension, okay? Which is what we find at the transition, but the symmetry somehow dictate that this is true in the gapless theory. The gapless phase does not apply to our transition, but and in this theory we do not find a continuous transition, or we have to say that maybe this first order is actually a result of classical continuization. Maybe when these guys are just starting becoming relevant and when they compete, maybe there is a continuous transition in which we don't know. It's not a theory that we can treat. Okay. Now, unfortunately, we suspect that the transition is actually first order, and while the reason we suspect so is that actually on the phase boundary, along with U1 symmetric line, we notice that the critical point is at exactly 2. So we find it numerically, and at first it was close to 2, and then we studied very carefully, at all cuts we studied very carefully to 3 or 4 digits of location. And this was 2.0 to 4 with 4 zeros, okay? And you suspect that it's solvable, and we looked through the literature of integrable spin 1 models. There are only a discrete number of them, and it is this model indeed happens to be one of them, okay? And this model is related to some vertex models. Actually, there is a Q-state generalization of integrable model, and this is how this integrable model looks. If I write the operators in the Ken-Bra basis, and this was solved actually in the context of this model is where this inversion trick that when Baxter used extensively was developed, where you do not use bad answers, but you use computing transfer matrices and analyticity properties to it's super very constraining and learn about the eigenvalues of the transfer matrix. So it was for other purposes, with a lot of information was done by Klumper in 1990, and Klumper found that this model has a finite gap and a finite correlation length, and he found closed form expressions for these. These are some look complicated, but these are related to some elliptic functions which always appear in these integrable models. And Klumper concluded that it's gap, and he guessed that it's probably in the same phase as the model where there is this SU3 model or SUQ model, which I said is integrable and is in the DBS phase, because that one is also exactly another discrete integrable model. Okay, but now what Klumper did not calculate these values for question of interest, but he calculated them for Q equal 3 for our model, where correlation length is 200,000 lattice spaces. Of course, we will, for our DMRG, we will not, it will look continuous from well beyond what we can do, and one can kind of trace where this very large number is coming from, is that this expression becomes singular for when Q approaches 2, so our Q equal 3 is, you can see it's kind of close to this Q equal 2. And when we, one can cook up a walking RG scenario, just like this was done by Cardi and others to explain why 5-state Potts model has correlation length 3500. So it's so I can. It's basically if you postulate flow equations like this with small epsilon, you can have a basically in the regime where there are no stable fixed points. So this is where fixed points move off your real axis to complex plane. The vicinity of lambda equals 0 is still the flows are very slow. You do not run, you walk. And you can, if you are starting on the other side of 0, it takes you exponentially, it takes you 1 over square root epsilon to pass through 0, and converted to length scale, it's exponentially long length scale. And in the Potts model, 5-state Potts model, basically one knows this epsilon from the exact solution, one can cast exact solution in this working RG picture, and the 5-state Potts model, this epsilon is 1/10, which may be enough already to generate this correlation. And for our model, it looks like we are Q equal 3 is actually in some quantitative, it's like Potts model at 4.5, so it's even closer. So when you, and this closeness is one of the closeness is in the exponent, so that's how you can get even 2 more orders of magnitude in the correlation. Okay. So, and that's pretty much the story. I can tell in more details if you are interested. So from the perspective of complex CFTs, there is a little bit of difference from the, it can be cast in the same scenario as the Potts model, but it seems that the dependence on the closeness to the threshold is quadratic as opposed to linear in the Potts scenario. And we suspect that actually, so if one were to try to cast it into complex CFTs, that actually there may be more than one pair merging, and maybe this is related to that. So that's the story in a nutshell, and I can tell details to anyone interested.
Thank you.
And I'm just 4 minutes over.
Wow, that's impressive. So are there any questions? Yes.
So can you exclude that it changes on this, phase one continuous?
For us, it looked like we studied multiple cuts. So starting from about 0.3, you are away from this criticality. It's already nothing like this. It looks like some new type. But everywhere, 0.3, 0.6, 1, 1.4, everywhere it looked the same. Like same power loss, same central charge, no hints of any drifts in the exponents as we increase the bond dimension. But it could all be that it just, we are at 200, the bond dimension cutoff us gives length scale 200, and the actual correlation length is 1,000 times. It's 3 orders of magnitude larger. So this will look like, yeah.
So what is the Q equal 2 CFT? What are they?
Oh, Q equal 2 model is just the Heisenberg spin chain.
Are you saying the exponents of that?
Yeah, I don't know, maybe you can say central charge, or what we saw the central charge was 1.2, 1.2, maybe you could say it's close to central charge of the Heisenberg.
If you calculate this C for the Heisenberg chain, there are a lot of corrections. I think C equals 1.1 is probably, it's actually 1, but there are some corrections.
Yeah,
how about the
Don't know.
Like spin correlation clouds?
Well, I wouldn't know how to relate to. So these are the decay was not 1 over, the decay was slower when VBS order in Heisenberg is 1 over R decay. The decay here, the scaling dimension was 0.3, so 1 over R to 0.6. Yeah, maybe
Is that for the BBS correlation?
yeah, so here the exponents are these are the scaling dimensions. The ferromagnet and BBS have actually the same scaling dimension 0.3.
Again, if you do it in the Heisenberg chain, there are log corrections, so it's very hard. Unless you know about the log, it's very hard to see the correct exponent.
But yeah, you actually you see pretty close to 1 over R if you are.
Well, you actually see something like 1 over R to 1.2, so you know.
Yeah, maybe.
But that's a big difference.
That's in the other direction.
If there are no more questions, let's thank one more time. We have next talk is tomorrow at 10. You can get coffee starting from 9 or discuss or chat. And now we can also go to a pub or something. So, thank you.